how do we leverage text to enable next generation of enterprise applications.
Hi, everyone. My name is Kun. I'm a research staff member at IBM Research. I'm also a former banana slot. So I graduated from UC Santa Cruz in 2017. After getting my PhD, I joined Yunyao's team in Almaden. Have been working on human-in-the-loop machine learning and NLP.
Okay, I guess we can get started. So hello, everyone. Very nice to meet all of you. Hope I can see you in person someday. Today, Quinn and I were going to present about the work done by a larger team. It's on building domain-specific knowledge base with human loop. So I will first give a high-level overview of different projects in the team on this topic, and then Quinn will dive into a little bit more details on a couple of the specific projects. So while we are presenting, feel free to interrupt and ask questions. I will also ask people to ask questions in between, and I hope at the end we will also have enough time for discussion. But in general, let's make it as interactive as possible. So don't feel hesitating to ask questions, okay? So as I just described, right, our focus is on enable next generation of enterprise applications. So what are the enterprise challenges? This is actually quite different from some of the challenges when people think about NLP research. So the first challenge is customizability. It is very important to build a model that works out of box, but at the same time, for most of the customers, they have very rich domain that we need to somehow incorporate the domain knowledge in the model we are building for them. And the underlying content can also change. So we cannot build things once and forget about it. Instead, it's a very evolving process where we need to do customization from the beginning, as well as providing ways to do customization on an ongoing basis. The second part is explainability. So explainability is a very hot topic these days. You can see multiple workshops about how to interpret the black box model. There are also tutorials on explainability. In fact, Quan and I were going to give a tutorial very soon at the ACL about explainability on NLP. But in general, in the enterprise environment, for various reasons, from regulation to actual engineering requirements, we need to be able to explain the rationale behind the prediction and reasoning to experts. The third challenge is learning from less. So a lot of time we think about, oh, there is a big data problem, but often in enterprise, we have small data problem in the sense that labeled data tend to be very expensive and very small. In some cases, we may not even be able to get unlabeled data. So for example, if I'm building a service to do PDF conversion as an example, right? I may provide a service, but the customer not going to share with me ahead of time what are the labeled data or unlabeled data they have. But they expect whatever we build works out of box nonetheless. The fourth challenge is the quality assurance, especially when it comes to building knowledge base. A lot of decisions will be made based on the knowledge base. So how can we provide some kind of guarantee on quality is a really big challenge. So in the rest of the talk, I will address different aspects of these challenges as we go. But the general approach we're taking is that for the main problem we're trying to address, we define something specific for that domain. So we call domain-specific language for a particular task that provide very powerful primitives through very powerful machine learning algorithms and so on. Then we leverage neurosemantic AI with human-in-the-loop, try to build interpretable models with a variety of explainability. So this is a general approach we are taking. So in this talk, we're going to use a particular example on how do we piece all these things together to build a domain-specific knowledge base. So the particular use case is how do we create data as service in the financial domain, where in this domain, the rich set of data source from public data sets such as SEC, FFIEC, right, all this regulatory finding, and to be able to identify company fundamentals, including the key personnel information, financial metrics, industry KPIs. So the challenge, as you can see here, besides what I just talked about earlier, right, there is a volume challenge, the more than 15 million reports, and it's growing, as well as continuous new data comes in, because every single day you can see new data comes in, because companies are required to file financial reports for different reasons, and there's a larger variety of forms for different purposes. So in order to build a domain-specific knowledge base, we need to extract and integrate knowledge from this vast amount of data, and in the end, be able to support decision. So you can look at our VLDB demo paper for some of the technical details. So here I will also describe a few of them. So once we build such a knowledge base, we're able to solve much more complex business problems. Think about, for example, within our industry, how do I compare performance across the industry for all the competitors? So I can, once we build this knowledge base, we can compare the key performance indicators across the industry. That is very meaningful for them, right? If you think about, as a general non-domain expert, when we think about performance of a company, we will think about profit and revenue, right? But this is not the most important numbers for our industry. Like for the airline industry, that particular key performance related to passenger mile. For natural resource company, they have other performance indicator. We can also identify counterparty relationship, non-exposure, all of which will help us better understand the risk level associated with different companies. So for example, if you think about 2008 economic crisis, right? Much of the crisis is that because of the complex financial instrument, a lot of companies expose themselves to unnecessary risk due to this kind of non-exposure. So I'm going to describe a few specific instances where we use to construct the knowledge base. So one is I mentioned about the long exposure, right? So this is actually a non-trivial task. So if you think about extracting information of the bottom table, like I want to identify who are the company involved, what's the role, what is the commitment. Now we need to have some technology that are able to read through hundreds of pages, identify the corresponding company and the role, as well as the corresponding commitment amount. So as you can see, there is no one single table from the original document contains information. Some are in semi-structured format, some are in plain text, some are in tables. So we need to put all of them together into one single table. But also remember, the loan agreement changes all the time, right? So what works for this particular document may not work for the next one. So we need to build something works regardless of the format of the original document. Then similarly, in order to identify key personnel information, we need to be able to extract information across different documents and link all the information together. For example, if I want to identify for every single insider, the employment history, I need to be able to go to different documents, like for example, look at the signature of a document, look into the job title, look into the bibliography for the particular person, identify the employment history, and also look at the particular tables to look into the committee membership, also identify potentially, compensation information and so on. So the challenge is, how do we know how those findings refer to the same person? There is no unique keys, right? So the same person's name can also be referred to slightly differently across different documents. And then the supporting attribute also vary based on the context. Like for example, in here, we know there is a person name, there is a job title, then in another place where it's slightly different. So it's, in general, it's a very challenging problem to do integration. So Qian will actually spend quite a bit of time in today's talk and describe some of the work we have done that will help do this kind of entity in resolution. Another thing is we need to construct structured knowledge, not just from plain text, because when we talk about natural language processing, a lot of time you think about plain text where you perform information extraction. But in order to handle complex enterprise data, we also need to be able to understand semi-structured data like the XBRL file here, as well as semi-structured content within textual data like the HTML file here. So we need to be able to understand this particular metrics is actually this one, and then we are able to link them together. So think about it, this is almost like some kind of ontology with a very specific domain-specific meaning that we need to link to a particular mention of the corresponding entity in the financial document. So as I described to you a few challenges in building the knowledge base that I showed at the earlier part of this talk. Now we're going to go through each of the AI life cycle, kind of tell you corresponding challenges and the solutions that we have. The first one is the first part of the life cycle is document ingestion, as I described earlier, right? One part of it is a lot of different kind of documents. So we need to be able to ingest a large amount of document, but not only that, often the document we ingest are not in machine consumable form. Think about the PDF document is one type of very significant enterprise document format, right? But for PDF, even though manually we can easily understand all the PDF documents, for our machine, it's actually very difficult. The raw PDF information contains characters and then position of the characters, graphic lines, font, and image information. So in order to understand PDF document and reconstruct in that way that a machine can understand, we need to infer from those kind of low-level features to understand, okay, this set of text are actually a column, this block is a table, and then this is title, this is header, this footer, and so on. And also, there is no standard on how do you create PDF, right? So the wide variety of PDF formats across programmatic PDF as well as scanned PDF. So in general, PDF is a very hard problem. Everybody working on it can understand. Here, we just give you some high-level overview. The particular focus from my team is on table understanding. So basically, given PDF, we can do first level parse, identify the rough document structure. If the document is scanned, we will first go through an OCR engine and get the character information out, and then we do the parsing. Then we parse some of the high-level structure information into table extraction capability, which will then identify table boundary, cell boundary relationship, and finally assemble all the information together to reflect the original document structure. So why table understanding is hard? It is hard because of wide variety of PDF table. So here are some examples. I will not go into every single table, but just give you some high level view, right? So we have table with graphic lines, that from human point of view, very easily understandable. Then there are also table with visual clues only. You basically kind of need to ask the machine to understand the white space to be able to do the segmentation. Then we have more complex tables where we have nested header and we have multiple lines above the divider. So somehow we need to identify whether this is also one table or two table. It's actually very debatable. Then we have a multi-row, multi-column header table where we need to understand how do we split them out, what's the corresponding hierarchical relationship. And then we have tables with text and charts, tables with textual content. So in general, table understanding is a particularly hard problem for PDF. So in my team, we have been working on table extraction for a number of years. And in the past 1 year, we actually made a significant progress by leveraging some of the techniques from computer vision into table extraction. So this is a very high level view. But the general idea is that in general, for table extraction, the high level task is identify table boundary and then identify the cell boundary. So instead of do it in a pipeline fashion where we identify the table boundary first and we identify cell boundary, we do it in a more loosely coupled stage where we basically try to do both at the same time. And then we will re-rank overlapping detection and then adjust the table boundary output as well as the cell boundary output. Then similarly, once we have the detected table, we can do additional cell boundary detection. So the first level of cell boundary detection is a very rough level. It mostly try to improve the table boundary detection. But once we have a very good table boundary detection, we can now do much more high quality cell boundary output. So this is a task where we have done some comparison over publicly available benchmark data. If you see here, our result is very comparable, if not better than state of the art. But the most important message is actually the following. Even though our advantage on public benchmark data is quite evident, but it's relatively small. However, when we use metrics that actually better reflect in downstream processing, our advantage is much more evident. So I don't have time to go into this today, but if you recall, for example, look into this year's ACL Best Paper Award, right? It's all about evaluation. So when you work on NLP or any kind of AI task, it's really important to understand what are those metrics reflect. What matters is not necessarily doing the best on those metrics that people publish in a paper, but really design metrics that reflect the intent of the task that matters to your application. So I talk about domain-specific knowledge-based creation, right? Then what do we define as domain knowledge? So I'm going to give you a few different level of domain modeling. The first level is domain schema, right? When we create a knowledge base, we will understand what are the key entities, the relationship, attribute of the entities that matters. The second part is constraint. What are the general relationship or constraint that we can assume it always hold true? So when it comes to constraint, there are two kinds of constraint. The hard constraint where it will always be true. For example, for a common insider, the start date of an employment must be always before end date. If this is violated, then something must go wrong. The second part is soft constraint where it may be true most of the time, but it could be violated in a very legal way, depending on particular scenario. So I will describe, how identify those constraints can be helpful for us to be able to do quantity evaluation at a scale. And the last part is the vocabulary. So when we think about vocabulary, in the case of dictionaries and so on, it may sound very simple, but it's actually very critical from domain modeling point of view. So here I have some examples, right? Like for example, the different ways to refer to bank revenue, total interest income, total non-interest income, and so on. But the challenge is there could be metrics with different names that is actually the same metrics. And then we could also have metrics that differ only slightly, but actually means different things. So we really need to understand the domain vocabulary to do a lot of the extraction and integration. So once we digest the document and convert the document into a format that is machine consumable, we can now do understanding for individual document. So we have an ongoing project called SystemT. It's a declarative engine to support text understanding for the enterprise. Some of you may have heard about this before. It looks very much like a relational database where we have a language called AQL designed very similarly to SQL. So you can express your algorithm in this language, which then will be executed, will be recompiled by our optimizer into our execution plan. And then the execution plan will then be executed by the operator runtime. So if you look at the right-hand side, this is a very simple relation extraction, right? So we already identified person, identify phone number. Now I want to say identify all pairs or relationship between person and phone within the same sentence where there is a particular clue in between. So it's fairly expressive, but also fairly simple. So this is a project that we have been working on for a number of years, but it doesn't mean we're working on the same thing. So in early stage of our project, we focus on the basic NLP primitive, syntactical NLP operators and so on. So these are very powerful in supporting certain use cases. But now most of our efforts actually focus on how do we build more advanced NLP primitives using techniques like semantic parsing, table understanding, so that we can better help building more complex use cases. So I will explain very briefly the two things, right? One is the semantic parsing, another is table understanding. So here I have two sentences, pretty much express the same semantic meaning, but if you look at the syntactical structure, it looks quite different, right? One is active voice, another in passive voice. So the posture looks different. But then if I turn both into a shallow semantic parsing representation, they will be the same, where there is the action chess and we know the tense is present, predicate the chess point one, the argument will identify the fox is the agent of the action and a squirrel is the target of the action. So now I abstract away the syntactical variance between the sentences, right? So this is a very nice abstraction that allow me to simplify building on top of complex NLP structure. And we want to do this for different languages. But in order to do that, we have multiple challenges. One is what's the right mini representation we choose? Right now we have different kind of mini representation for different languages, and even within the same language, there are different mini representation. So in our research, we have proposed a unified mini representation called the universal proper bank. So it's very much similar to universal dependency parsing, where we use the English proper bank annotation as a starting point and then extend it across different languages. The second part is building the model. If you are familiar with SRL task and dependency parsing, you will understand dependency parsing has much higher quality than SRL in general. The reason is that for SRL task, we need to address uncommon frame issue. So for the same frame, many of them only appears a couple of times in the training data. There are a lot of low frequency exceptions. So today I will not have time to go into the details. But I encourage you to, for example, to check out our instance-based learning paper, as well as some of the talk I have given before on towards universal natural language understanding. The third challenge is language expansion. So if we have a perfect path for English, we're still not solving the problem, right? Because in the world, there are over 7,000 languages. So how do we expand the capability to other languages? The challenge is high quality data is very difficult to obtain. And often there is language specific annotation. So it's very difficult to borrow information from high resources languages to low resource. So we have worked on this problem for a number of years. The general approach we took are two things. One is we want to have a way to automatically generate the data as much as possible or reduce the requirement on scale. So we have a number of papers in this direction. Another thing we started recently is also try to leverage transfer learning and to do cross-lingual transfer learning better. But the goal is the same, you know, how do we reduce the effort required and maximize the quality? So once we have universal natural language understanding, there are many things we can build, such as, you know, we can write equal once and the statement can run on top of sentences from different languages. We don't need to worry about the difference between the language. Like here, for example, I want to identify purchase relationship. I can only write two very simple statements where I'm looking for a sentence where it contains the purchase verb, and then I want to return A0 and A1. Then I can identify the purchase relationship, right? Or the by verb, and then what they purchase, whether the intent is affirmative or negative. And the one I just show you is just an academic example, but we actually have utilized this semantic understanding, what we call semantic linguistic structure, to build transparent linguistic models to understand contract. So this is actually a real product in Watson Discovery. So what we do here is the following. Given a contract, which is often in PDF, by the way, we first do the document conversion. Then we go through the NLP pipeline where identify the element you can think of as a sentence. Then for every sentence, we try to classify what's the category of that sentence. And the categories are predefined based on legal knowledge. Like for example, here, the user want to say, I want to find from contract all the elements that is talking about pricing and tax. So let's say for this one, it has been identified as pricing and tax. In some cases, we may make mistake. Then the user can also suggest changes. So this is at a high level, this is what we do with the semantic understanding. And another thing we also do is understand the semi-structured data like table. So what we do there is for every single table, we want to, in the end, construct a data self-centric view so that we understand for every number here, what's the meaning, right? So instead of this form, we want to say, okay, for this table cell, this is column header, row header, some context information, and we also even want to normalize the context. In order to do this, what we need to do is to identify for every data cell, the corresponding column header, as well as the row header, including the hierarchical relationship. Like here, for example, if you just look at the row header, it's only passenger, but if you only know passenger, this is not meaningful, right? You want to know this is operating revenue related to passenger. And then we also want to know the context, right? Like here, for example, what is the meaning of 3716? Here we will know this is Canadian dollar in million, and then there is also unit of the dollar sign. And then we can further normalize the third quarter into code 3 so that later on the upper level application can do the processing much more easily and get rid of the variance from the original text as much as possible. So by having this kind of out-of-box table understanding, we were able to build a COVID-19 dashboard in less than a week in early this year, in late March this year. So if you are using your iPhone or if you go to weather.com, you can look at, there is a COVID-19 dashboard. Behind the scene, a lot of the information were obtained through the table understanding capability that I just described from the data set published by different counties, because some counties they publish data using CSV file or using some kind of API. But a lot of the information are only available in HTML or PDF, especially at the early stages of the pandemic. So this is really a very powerful technology that, because we're able to understand table out of box so well, building a COVID-19 dashboard become a much simpler task than before. So I have talked about all these abstractions, languages, and so on. But think about people like you, right? Maybe you don't want to necessarily want to learn a new language. You are comfortable with Python. You want to do something for your task, but you want to learn as less as possible, right? So depending on specific scenario, we build tooling for different users. So we have Eclipse tooling for AI engineers who's very comfortable with programming and they want to write very powerful models on top of SystemT. So they have a full-fledged IDE. And then for other people where the user scenario is simpler, then they can use the visual IDE to do the task. For subject matter experts, this is actually our key target right now. We want to support them to do extraction by example, or we can learn rules in advance and then interact with a human so that they can give us additional feedback and co-create the final model. So if you are interested, you can go to the URL here and look at some of the online demo. And in the end, another thing that is important is when we build a model, it's very important to understand how well a model works. If there's an error, where's the error, how to improve the model based on error analysis. So we have also done work on helping AI engineers to be better able to systematically understand the errors and do model improvement. Okay, so I'm going to pause here a little bit before I move on. Any questions, comments so far?
Hi, Yunyao, this is Adwait. Yeah, I have a question. So this was the data that, so the COVID dashboard you were talking about, this was a thing which showed up on the weather.com app. Is that what you were saying? Okay,
so,
okay.
Correct. So this is basically what we enable the one from weather.com. Okay,
okay, great. Yeah, I use that app too, so I'm familiar with that dashboard. My question is that, was that, that seemed like, was that implemented all throughout the country? And if so, how did you account for all of the different table formats that might be published?
Yeah, so that's a very good question. So in general, the two parts, right? One is identify, the relationship between the data cell as well as the column header, row header. And then the second part is actually extracted out based on different specific table. So what people have done in this particular case is we write a general module, try to identify the key information as much as possible. But then for cases where there's specific customization need to be done, then we build a customized model for that particular type of table.
Okay.
Yeah, so there are, automatic method as well as manual effort. So we need to, this is part of when I talk at the beginning, customization. We basically need to make customization as easy and fast as possible. Because in those cases, it's impossible to build something work out of box for everything.
Right. And just to follow up this idea of parsing tables. Just so I understand, does your technology like look at the graphics on the PDF page itself, or do you first pass it through some type of OCR, so it's already kind of given to you in character units?
So you can think of the following, right? First of all, even for the COVID-19 use case, we have data in PDF, some in HTML. So the first step is basically convert PDF to HTML. But you can only get to this level where you can know, okay, there is this is a cell, and then this is corresponding column. This is corresponding column above it. This is the column next to it. So just identify which is data cell, which is header cell itself can be a very hard task.
Yeah.
And then identify, the hierarchical relationship, right? In the row header and column header is another challenge. So I think we are exploring in some cases, we do end-to-end, where we go directly from PDF to table understanding. But it can be useful for some cases, but the table understanding from HTML is still necessary because a lot of the data we get is in HTML format.
Right, but let's take the case if there were if in the original PDF there was some type of graphical annotation, like for example, imagine if a cell was circled and there was a little call out saying some comment about the cell. Like, is the technology possible to put that in a structured form or not yet?
It is possible. It is possible.
Okay.
We can. I mean, it makes things much harder, but it is possible that when we capture a table, even table cell, we can capture also the metadata for the table cell. Yeah.
Okay.
But that's a very good question. It's actually can be arbitrarily complex. So right. A lot of time I would say table understanding or PDF understanding is actually harder than understanding natural language. Because in natural language, right, we have a rule. We have some kind of grammar, right? But when people creating table, there is no rule. People can put things in whatever way for whatever reason. It's very complex. Yeah.
Yeah. Okay, good.
Yeah, so that's the beauty of the real world task, right? It's very noisy.
Great. Any other questions from the speaker, from the audience?
Yeah, it's, so for continuing off of that question, you showed that you use like computer vision as well to look for grid lines. How do you do that? Is it first converted to something, or do you take it as pixels from PDF?
So we're using techniques from computer vision, right? Because when we get a PDF, it's essentially a mixture of characters and an image, right? So basically we have an image and then we have the characters position on the image.
Yeah, oh, okay.
Yeah, so even though to our eye, there is no difference between PDF to a great extent to Word document, but how the data is represented is quite different. Yeah. Thank you. Any other questions, comments?
Yes, I have a question.
Sure.
When we deal with multiple files and we try to extract information among multiple files, it's a little vague for me how we can compile the whole things into the same knowledge, how we can make the connection between all of them.
Yeah, so that's the next step I'm going to talk about. So far I talk about, getting document consumable, understand individual document. The next one is entity resolution. I will talk at it very briefly here. Kun will dive deeper. But on the high level, it's the following, right? Basically for every single document, let's say we finish the extraction, we turn the document into some structured form, right? Now we want to say, okay, identify these two companies, for example. I identify Isabella Bank In another document, I identify Isabella Bank Corp. Now I want to say, is this the same company? If that's the same company, I can merge them together, right? You can almost imagine I have a small graph here, I can small graph there, I can merge them. But I first need to make that determination whether they're the same company. Similarly, in one document, I may identify Bank of American NA, in another one is Bank of American National Association. Here I need to identify whether they are the same company again, right? So it's a very challenging problem again, because you cannot just do that based on the surface string, like the example here, right? The second example, it's only differ by 5 characters, but the second one differ by much more. But the first one is not that much, the second one is that much. We need to understand the domain knowledge, because when it's a bank, like when you say something bank, it's a bank, but if the bank corp is actually the parent holding company, so they can never be the same regardless of the closeness of the string. On the other hand, in the second case, we know NA is abbreviation of National Association, therefore they are equivalent. So we have some algorithm that can figure out these details of the semantic structure of the entity, and then we take that into consideration when we do the match. Similarly, when we compare the location, right? Like we know abbreviation of the California is CA, therefore we know they can all be CA. Quinn going to talk more details about the tooling we have. On the high level, we basically also try to have human in the loop, but do as much work as possible with machine learning. So Quinn going to talk about both. So I'm going to skip through this. Yeah, so hold on for Quinn's talk on that topic. Great question. So now, assuming I already did the extraction, I do the entity resolution, I link everything together. I now have a knowledge base, right? The biggest question is, how good is my knowledge base? So the challenge is for in the real world, right? We don't have ground truth for the knowledge base. You cannot say, okay, now I compare with my ground truth, my test data, and I can have some number. So we cannot afford to do that, right? Remember, we have the multi-million nodes, right? It's impossible to create a ground truth for those. So instead, we take a few different complementary approaches. One is we use the data assertion, and based on whether the assertion pass or fail, we can decide whether there's a quality problem or not. And we also need to allow the case where if there's a problem, we don't want to completely start from scratch. So we have this complex flow, right? We want to say when one of the stages fail, we want to keep whatever happens before and restart from the part where it failed. So to give you an example, so we have talked about this earlier, right? We talked about the data constraint. So I can turn the data constraint into something to do data profiling. For example, every single time after I finish a run, I can check whether I feel different things. Like first of all, whether every company has a CEO, right? If that is violated, it may or may not be a problem. So for example, this is actually a real case where we found Build-A-Bear does not have a CEO. They have chief executive bear, but that's not wrong, right? However, we cannot identify whether it's wrong or not until we look into it. But the beauty of doing this kind of profiling is that we can identify the needle in a haystack problem, right? By leveraging the domain knowledge. Similarly, generally a company should have one ticket symbol, right? But in some cases, we may find, okay, the ticket symbol changes, then we need to find out whether this is really expected. And in other cases where we know number of companies is the same across different runs in general, but in one case, maybe we find, oh, there are 2 companies added, then we can see, oh, there are 2 companies actually gone public in the past quarter, therefore this is expected. So basically we need to have like small number of curated ground truth where we can do evaluation, but we also need to have data assertion and profiling that examine the data at a much larger scope. And by the way, this is a technique not just for this quantity evaluation for knowledge base. This is a technique that is true for pretty much all the NLP tasks. So you need to think about, given an NLP task, what's a general assumption it would hold true if everything goes right? And you want to implement that safeguard in your evaluation, regardless of the actual task. The guard may be different, but this is a very important technique that often we don't think about it when we work on academic paper because you have benchmark data.
I have a question about this.
Sure.
Is this something that IBM does, or is this something that the customer who purchases your tool does?
So this is, so in this particular scenario, right, we provided data as service. So this is what we do. We basically, before we make the data available, we do all of those to provide a certain level of quality guarantee.
Gotcha. And are all of these constraints manually created?
So that's a very good question. We create some of the constraints manually because based on domain knowledge, like based on the ontology, we can define some constraint we know. Another thing we have been doing is also actually identify some of the constraints automatically and then ask the domain expert to validate. Because sometimes you may find a certain trend in your data, but it may be just accidental, right? So we also do that mining, but then ask a domain expert to do verification.
Okay.
Yeah.
So that's a fairly manual process.
It needs to involve some human. Yeah. But I think once you have the constraint, then most of it can be automated. So you only need to do it manually when there's a violation for the soft constraint.
Okay.
Yeah.
I had a question. So
sure,
what is the typical life cycle time for these sort of processes for like going through the whole set of steps? Because I'm assuming that a lot of the improvements might be reducing that time significantly.
Yeah. So it really depends. I would say like for the particular example I will talk about for the financial knowledge base, right? Once we have everything, like all the backend build and everything running, the actual production life cycle is twice a week, where we can quickly run the data evaluation, like we finish the run maybe like within 24 hours, right? And then we can do the evaluation. Typically going through the assertion, profiling, failure will take maybe another 24 to 48 hours. In general, we can do 2 runs every week.
Okay, that's actually pretty impressive, like going through the whole process so quickly. Yeah,
so I think, but there's still a lot of things can be improved. This is why we also have some research on identify errors. So the biggest challenge is the following. When something fails, right? Let's say, for example, for whatever reason, now I have some null value, right, for my metrics, but it's a very complex workflow. How do I know where it is, right? So we also have this visual diagnosis tool that can help us to narrow down to a specific component. So the challenge of such complex system is that a lot of time for individual developer, you don't necessarily understand whether your result is correct or not because you are not domain experts. And then the domain experts only see as the final output, right? So only at that stage, they can identify the mistake. So now how do you translate that knowledge from domain expert to be able to go to a particular component to say, hey, you did a join wrong or there's something's wrong. So that can be, depending on specific error, it can vary, we can solve the problem maybe within a day, or maybe we need to have an entire sprint to sort it out. Yeah. But basically tuning is very important. Similarly, like what I described earlier, right? For specify the constraint, again, research can be very helpful in actually identify possible constraints for the domain expert to verify rather than they have to specify it themselves. Yeah, so when we talk about a human loop, a lot of the time is really about how do we get the human to provide input at the critical moment so that we can minimize the effort, but at the same time, maximize the quality of the system. So the last stage of the whole thing, right? Once we build a knowledge base, we can enable programmatic API, natural language interface, and also we can even embed the knowledge base so that we can use it for other tasks. There's a lot of recent work about knowledge base embedding, right? So I will not go into the details, but on the high level, I want to summarize what we just talked about, right? Throughout the entire life cycle, when people talk about human loop, a lot of time, in fact, if you read some of the recent paper, it's basically about active learning at data labeling time. But a lot of work in my team is actually beyond the initial stage of reducing data labeling. So it's both about how do we potentially enable people to build the explainable model directly through IDE, or we can learn a model in a language that a human can manipulate and then co-create the model, or we can leverage transfer learning and active learning to reduce the label data. And another part is also how do we learn from feedback and utilize the feedback to influence the entire AI life cycle. With that, I think that's the end of my part. Before I finish, any questions, comments, before Quinn can talk more details on entity resolution? Okay, Quinn, you can start.
Okay, thank you, Yunyao. Let me share. Can you see my screen now? Can you see my screen? Yeah, okay.
Yeah, I can see the screen. Yeah, thanks.
Okay, thank you. So hello, everyone. My name is Kun. I'm very happy to have this opportunity to connect with all of you at Santa Cruz. So for the rest of the talk, I will dive into some of the concrete techniques we have for the entity resolution component in the AI pipeline that Yunyao described. Okay, so entities are essential to many AI tasks. For example, knowledge bases is basically a giant graph describing the different relationships between different entities. Entities are also highly used in information retrieval. So based on Google's statistics in 2016, most of the search queries sent to Google search engine are basically entity names. And entities are also highly used in data integration, which aims to provide a unified view of entities coming from different data sources. Right? So one of the important entity-centric problems is the problem of entity resolution, which is a task of identifying and linking different representations of the same real-world object across one or more data sets. For example, one entity resolution task could be matching Twitter user profiles with Walmart customer database. If you haven't heard about entity resolution, you probably have heard some of the other terms, such as reference reconciliation, merge-purge, record linkage, deduplication, entity matching, etc. So this is very ironic because we need to perform entity resolution for entity resolution. So although the definition of entity resolution is very simple, real-world entity resolution problems can be very hard because entities are very ambiguous. Here's a simple example. We are given a simple query entity, which is a person entity. It has 3 attributes, with name being MJ, location being United States, and date of birth being February 1763. So we are also given 3 candidate entities with 2 Michael Jordans and 1 Michael Jackson. So based on the information available, it is very hard to tell which candidate entity is a match to the query entity, since some of the crucial information is missing. And the sparse attributes and missing values are very common in real-world scenarios, and that makes entity resolution very hard. And however, if I give you the date of birth information of the candidate entities, our brain can do some reasoning. For example, we realize that entity one is a match to the query entity. Note that the reasoning process in our brain is rather complex, because if we look at the surface forms of the attributes, the query entity and the entity one are quite different to each other. One has Michael Jordan, the other one has MJ. And one has February 17th, 63 in text, and the other one has pure digits like 1963-02-17. Remember, we are trying to design an algorithm to solve this problem, and it remains a hard problem to machine, because if we simply use textual-based similarity functions, such as Jacquard similarity or at distance-based similarity, they would give us a very low score to this entity pair. So even if we are given the complete information, it remains a non-trivial task for a machine to solve this problem. Therefore, we need more powerful weapons for this problem. For example, before we compare the two entities, we can first normalize some of the attributes, such as normalizing the date of birth attribute of the two entities to a standardized ISO format, as shown in entity one. If we can do that, we can then safely use textual-based similarity to solve this problem. And this is known as entity normalization process, which is very crucial for many entity-centric tasks. Okay, so when we design entity resolution algorithms, there are several requirements for good entity resolution algorithms. And oftentimes, these requirements are conflicting to each other. Concretely, the model should achieve high precision and high recall. We also want to make sure that the model is somehow reusable, because training such model can be very expensive. It would be nice if we can reuse some of the assets. Next, in most realistic scenarios, we may not have any label data, or we only have very few label data. So in such case, how can we still learn a high quality model? We also want to make the learning process as automated as possible, since the whole pipeline is very labor intensive and very expensive. And when designing the model or training the model, we want to use models that have high expressive power, because the entity resolution problem can be very complicated, and we don't want to use a simple model to address a complex problem. Finally, explainability is also very important. Since in many scenarios, we need to provide explanations to the predictions made by the AI model. And fortunately, we have different techniques to address this issue. For example, active learning is a very effective approach to learn high quality model from small label data. Basically, the idea is that we let the machine and the human expert work together, and the human expert will guide the machine learning algorithm to generate better and better models through user interactions. And to address the small label data issue, we can also use weak supervision that can automatically generate more label data without or with very few human supervision. And for generate reusable assets, we can use transfer learning, right? So we can first make sure we are learning a transferable model that we can apply to other similar scenarios. And for bringing automation and the high expressive power, deep learning is a good option. And for explainability, you can either directly design a black box model or use some post-hoc approach to explain the prediction made by the black box model. Or you can carefully design your algorithm or your neural net so that it directly generates explainable models. So in the past few years, our team have been using these techniques, sometimes combining multiple of them to solve the entity resolution and normalization problems. So in the rest of the talk, I will talk about two of our recent work that use deep learning to solve entity resolution and normalization problems. And before I dive into the concrete work, I would like to ask the audience if you have any questions. Okay. Can you still hear me?
Yeah, I think the audio is fine. Any questions for the speaker, or should he continue? Okay, why don't you go ahead? Okay.
Okay, so for the rest of the talk, I'll first talk about entity resolution using deep learning and active learning and transfer learning. And then I will talk about how we do entity normalization and variant generation using deep learning and weak supervision. Okay, so first about low resource deep entity resolution with transfer and active learning. And entity resolution is a long-standing research problem, and the research can be traced back to 1960, where people started using rule-based approach. And at that time, people usually use manually design the matching rules to match entity across different data sets. And since 2001, machine learning has been applied to automatically generate the rules from label data. So this is good, but for traditional machine learning, it relies on feature engineering. Basically, a human expert has to sit down and design different similarity functions and matching functions so that the machine learning algorithm can use them to produce rules. And recently, in the last couple of years, deep learning has been used to solve this problem. And one of the benefits of deep learning is that there's no need to do feature engineering. So this is very attractive. However, deep learning is known for data hungry, right? So we have done a very simple experiment where we train a deep learning model to match papers between DBLP and Google Scholar. So it's a very simple task. And from this chart, you can see that unless we provide deep learning enough, in this case, more than 7,000 examples, unless we provide that many examples, deep learning, the performance of deep learning is actually much worse than other traditional machine learning algorithms, especially when we provide less than 1,000 labeled examples, right? So from this simple experiment, we know that getting label data is very important for a successful deep learning approach. But requiring large amount of label data makes applying deep learning to entity resolution very hard because first in realistic entity resolution problems, we may not have any label data. And in general, entity resolution problems have very low matching ratio, which means that it's very hard to find the positive examples for training a deep learning model. Take the Walmart Twitter scenario as an example. So the Walmart customer database may contain about 100 million records, and the Twitter profiles may have more than 1 billion records, right? So even if every Walmart customer can be matched to one of the Twitter profiles, which is very unlikely, the matching ratio is at most 1/10 to the 9th. So it's very, very low matching ratio. It means that if you want to randomly sample examples to label so that you can create a meaningful training data for the deep learning algorithm, and this task will fail because if you randomly sample most of them, I think most of them will be negative examples, but you need positive examples to train a deep learning model, right? So this leads to a solution that we propose. We actually designed a framework for low resource deep learning, deep entity resolution, where we combine two orthogonal techniques. One is transfer learning, the other one is active learning. So transfer learning has a very simple idea. So you may, so you have a target scenario possibly where you don't have any label data. And so in order to solve this problem, you find a similar scenario where you have a lot of label data so that you can first train a model in the high resource scenario and transfer it to the low resource scenario, right? You just need to make sure that the model you learned is transferable, right? So for example, for the entity resolution problem, a concrete example is that, for example, if our goal is to match papers between Google Scholar and the DBLP, where we don't have any label data, we can first learn matching model from another scenario, Google Scholar and ACM, where we have a lot of label data, and it's quite similar to the Google Scholar versus DBLP. So you can first learn a model from the source scenario and directly apply it to the target scenario without any further fine-tuning or further customization. So that's the spirit of transfer learning. And active learning is that before you, once you have the transfer model, right? So you can either directly use it to make prediction, or you can further refine it using the label, using the example carefully selected from the target scenario, and ask the user to label them, and to help the transferred model further adapt to the target scenario, right? So active learning is very effective in terms of fine-tuning the model so that the model is achieves very good performance over a specific target. Okay. So typically an entity resolution pipeline consists of series of steps.
I had a question. Sorry to interrupt.
Sure.
On transfer learning, how much overlap in like sample space or vocabulary is required for it to be feasible?
In general, there's no requirement. You can, for example, like every time you use like BERT or like fast text, you are doing transfer learning because you are using some pre-trained model and you can fine tune it, right? So I don't think there's a general rules that you need to find a domain that is very similar. But of course, if you can find a very similar scenario, that would be great. Because cool. in our cases that we actually hope active learning can do more things there, because it's okay that you may not have, because it's not very common that you can always find a similar scenario from that has a high resource, right? So that's why we add active learning so that we can further adapt the model to the target.
Yeah, and actually recently there's some work on transfer even across tasks. So people have been successfully transferred resources from tasks like, for example, text classification to question answering. Yeah, but as Chris said, you know, eventually you need some data of the particular task and data that are actually related to the particular problem you're trying to solve. Otherwise, it's very difficult to build a model that works for everything.
Okay, so this is, I was trying to say there's a typical pipeline. So first, given two data sets, we first need to do blocking, namely apply some blocking function, usually some similarity-based function to eliminate entity pairs that are obvious non-matches. So after blocking, we'll end up with entity pairs that may have a chance to match. Then the problem becomes a classic binary classification task. In this step, we can build entity matching models to classify entity pairs. After we get the entity pairs that the classifier think they are matches, we have another step to cluster the entity pairs. Note that it is possible that multiple entities on one side can be matched to one or more entities on the other side. So it's more important to resolve this before we output the final results to the user. So our work actually focus on the pairwise matching phase. What I'm going to talk next, we'll be focusing on the pairwise matching phase. Okay, so first, how can we learn a transfer model? So here we'll use a very simple example to illustrate our transfer learning idea. So assume that we have a labeled publication pair, hypothetically coming from two datasets, ACM and Google Scholar. For simplicity, let's assume that the two datasets have the same schema, consisting 3 attributes: authors, title, and venue, right? So how can we build a binary classifier for this matched entity pair? So here's our solution. So first, we perform schema matching to pair up entity pairs, attributes that we want to compare against. For example, for this simple example, since they have the same schema, we can pair up authors with authors, title with titles, and venue with venue from the two two records, right? After that, we then use some pre-trained word embedding, for example, fast text, to convert the textual value of one particular attribute into sequence of word embeddings. Then we use a ByGRU to process the sequence of embeddings, and finally get one vector representation, vector that hopefully capture the semantics of the whole sentence in this attribute. And here we are describing the model that we use in our ACL paper. In practice, ByGRU can be replaced with neural models such as BERT. So we do the same thing for the other author attribute to get one vector. In this way, no matter how many tokens each attribute has, we can convert them into a single vector. Once we have the two authors vectors, we compute the element-wise absolute difference of the two vectors to get a single vector, which intuitively trying to capture the semantic difference between the two attributes. We repeat the process for the other two attribute pairs to get title difference and the venue difference vectors. Then we compute the element-wise addition of the three vectors to get a single vector, which we call the record distance vector. Intuitively, this record distance vector represents the total distance between the two records. And once we have the record vector, we can build a binary label predictor, basically a multi-layer perceptron with the last layer being a two-dimensional layer used for predicting the labels. And then we can use the cross-entropy loss as the loss function and use back propagation to update the neural net, right? So I would like to mention that in order to make sure that the learned model is transferable, we use the shared GRU to process all the attribute pairs. This is to ensure that no matter how many attribute pairs the source and target dataset may have, we have no problem transferring it to the target model, target dataset.
Kun, quick question. This is Adwait. Are you using any pre-trained word embeddings in the GRU for the for the authors, for example? Yes, we're using fast text when we write the paper. But now you can use any pre-trained language model like BERT, for example. It's very, you just need to have a way to process a sequence of tokens and get a summarized vector that capture the semantics of the sentence. That's all you need. Okay, so right, so this is architecture we used, but we did something more. In particular, in order to make the transfer learning better, we adopt a domain adaptation technique called gradient reversal to improve the effectiveness of transfer learning using both source data and the target data. So the basic idea is the following. The proposed architecture contains three parts. First, we have this deep feature extractor part where we use a shared ByGRU to learn deep features that capture the difference between entity pairs, which is then sent to a feed-forward neural network to predict the labels. That is either it's a match or non-match. During the training, the goal of the green part and the blue part is to minimize the matching prediction loss using back propagation. So in addition to the label predictor, we also connect the deep feature extractor, the green part, to a domain classifier, the pink part, which is another deep feed-forward neural net, but we add a gradient reversal layer between the green part and the pink part. So the gradient reversal layer basically performs as an identity function that is we directly output what it received from the green part to the sent to the pink part, and doing forward propagation. And doing back propagation, it multiplies the gradients received from the later layer by -1.
So intuitively doing backpropagation, the output of the gradient reversal layer is basically leading to the opposite of gradient descent. That is performing gradient ascent on the feature extractor with respect to the classification loss of domain predictor. So the feature extractor will therefore be trained to minimize the classification loss of the label predictor, the blue part, and maximize the classification loss of domain predictor. So label predictor and the domain predictor will be trained to minimize the respective classification loss. So this is a way to use adversarial training to do domain adaptation. Basically, the idea is trying to fool the feature extractor, the green part, to try not to distinguish the source data and the target data, so that we can learn low-level domain invariant features for the matching task. Okay, so next, so I'll give you some transfer learning results from our ACO 2019 paper. So here we have tested on 3 different scenarios, and as you show here, what are the source data and what's the target data we're trying to transfer to. And here this shows that if we just use transfer learning without domain adaptation, this is the F1 score achieved. And DBOP ACM is a very simple scenario, and the F1 score is actually, if we directly learn a model from DBOP Scholar versus Cora and direct transfer to DBOP ACM, the F1 score is actually already very high. But we see, for DBOP Scholar and Cora, the performance is lower. If we add gradient reversal, basically domain adaptation that I just described, we can see that we have seen a significant improvement for the DBOP Scholar and the Cora datasets. And this is good because the difference between the first experiment and the second experiment is we only just add the training, add the target data to the training process without any actual labels, just trying to send more data, target data to the deep learning, so that the deep neural net is kind of familiar with the target scenario. We see this improvement. So this is good. However, we still see a significant gaps. So the red results in red are basically, since we have the benchmark data set, right? So we can train the deep neural net with the target scenario using the full training data. So this is the results achieved by the deep learning, so fully supervised deep learning approach using the full data. So we can see that for the last, the later 2 scenarios, we can see there's a huge gap there. There are 40% and 50% gaps there. And a natural question is, how can we close the gap there, right? That leads us to the active learning approach. So active learning, so this is a slide to summarize the basic idea of active learning. So active learning is a kind of an interactive learning. So you first start with some candidate model, and you use a candidate model. So you first start with some label data. Sometimes you may not have any label data. If you have some label data, you can first train a candidate model, use some supervised learning approach. And once you have the candidate model, you can use the candidate model to make predictions over the current unlabeled data. And from the prediction, you choose on certain examples or informative examples to be labeled by the user. And once the user annotates those examples, you will add those label back to the training data. And then in the next iteration, you refine your candidate model, and you repeat the process until the candidate model satisfies the user's needs. So it's not surprising that the most important part in active learning is trying to identify or design an effective active learning sampling strategy. So how can you find the most informative examples, right? So in our ACO paper, we use the entropy-based sampling strategy. We actually look for 2 types of examples. One is high confidence examples, and also we look for uncertain examples. So the idea is the following. So once we have the candidate model, we apply it to the labeled entity pairs, right? We then get labeled pairs. Then because the deep neural net will also give you the probability of the prediction, then you can rank the labeled entity pairs based on their scores, confidence scores. Then we first look for examples that have very high confidence score, and we call them high confidence true positives. We also look for examples that have very low scores and is in the negative end, and we call them high confidence true negatives. For these two types of examples, we don't ask the user to label them. We simply trust them. We trust the labels produced by the deep learning algorithm. And we can only do this because we first do transfer learning. If you have a random model to start, for example, if you want to directly use active learning from scratch, you start with a random model. And then if you use random model and use their high confidence true positive examples as a high confidence true negative examples, based on our experiment, there are many errors. So you cannot directly trust them. But in our case, since we are doing transfer learning first, we already have a reasonable model that usually give very good results on the high confidence end of its prediction. So it's fine to trust them. And also the benefit of this process is that we can automatically get more and more label data without actually asking the user to label them. And this is also very important for deep learning. And we don't want the user label a lot, right? So that's for high confidence example. For uncertain examples, we first look for examples whose probability score is just above 50%. So since it's above 50%, the model will label them as positive. But because they are close to the threshold, it's likely that they are incorrect. That's why we call them likely false positives. Similarly, we also look for examples whose probability score are just below 50%, and we call them likely false negatives, again, because their prediction score is below 50%, so it will be labeled as negative, but it's close to 50%, so it's likely that they are probably correct. So we get these two type of examples, and then we ask the user to label them. Once the user label them, we'll send them back to the training data to refine the candidate model, right? To give you some results for active learning. So this is, first we have applied this method to transfer a model and trying to adapt this to a data set called Cora. And first of all, the experiment we have done is that since we have the benchmark data set, we give SVM and deep learning all the training data they have. So there are close to 30,000 labeled examples, and we get the F1 score. So basically this can be seen as the upper bound performance of supervised approach, even supervised deep learning approach, right? So because they are using the full training data. Then this is our transfer learning plus active learning results. So if we use transfer learning first, and then we run the one experiment is that if we first learn a transformer model from a similar scenario, and then randomly sample 500 positive examples and 500 negative examples from the benchmark data set, the F1 score is only 84%, right? But still, it's also much better actually. With 1,000 examples, it's getting better and better. But with our approach, where we use first learn a transferable model, then we use our sampling strategy to get 1,000 examples, and every iteration we ask the user to label about 100 examples. So after 10 iterations, we stop the fine-tuning process, and this is the F1 score we achieved. So it's very close to the fully supervised deep learning approach, but the difference is that we only use 1,000 examples instead of 30,000 examples, right? So I hope this experiment can give you an idea why we think active learning is very effective and how we use them in practice. Okay, so this is a slide to summarize our entity resolution research within our team. We have been working on this for multiple years. And in 2017, we developed a system called SystemER. And this is actually quite a successful system because it has been applied to produce entity resolution algorithm that is already used in product. And also the difference is that SystemER produces expandable models. So it learns rules. You use active learning and rule learning to learn expandable rules. And we also have a few papers. It's very interesting. You can take a look at the video demo as well. And then last year, actually 2 years ago, we started using deep learning to solve this problem, which is the one I just described. And recently, we have been trying to use deep learning to directly generate expandable entity resolution models. And we are also working on entity linking. And hopefully we'll have some good results coming up soon. So this is the first part of my talk about entity resolution and normalization. Before I move to entity normalization, I would ask if you have any comments or questions.
Kun, just a note on process. I think the slot goes up to 4:15. So maybe right. Is there something? Is there some way maybe you could finish up or just like summarize the rest in like 5 minutes and leave a couple minutes for questions?
Sure, I think I can finish in 5 minutes. Okay, so to briefly talk about normalization and value generation. So I'm showing two examples, one for normalization and one for value generation. As you can see, that normalization basically take multiple different representation of the entities and try to normalize them into a standardized form. And value generation is the other way around. You are trying to generate different representations of the same entity expressions, right? So, and usually the entity normalization and value generation is done by entity linking. So you first identify the entity mentioned in a sentence, then you link it to a knowledge base, and then you use a knowledge base to either do a normalization or value generation. So we are considering a more challenging scenario where we don't have any contextual information or a knowledge base. So how can we do that? So our observation is that entity names usually have internal structures. So for example, I'm showing two examples here. If you know their structure representation, you can manipulate the structure representation to generate different variations or perform normalizations, right? So this is a simple example can show that this is a structure representation is useful, but there are some dark clouds because first, we don't have such kind of fine-grained model, fine-grained labels to train such model for us to parse the structure. Second, I may not have any dictionaries to capture domain vocabulary. For example, I may not have a company suffix dictionary to help the algorithm to identify the core domain vocabulary. And we may, and also, since we don't have label data, if you ask the user to provide a label data, providing such kind of structure label examples can be very difficult for the end user. And same for creating the normalization and value generation functions. So we developed the system that combines deep learning, active learning, and weak supervision, and human in the loop to solve this problem. So first, we invite the human to be part of the learning process to guide the learning algorithm. And as a screenshots of the system shows here, we develop an intuitive interface for human to easily provide labels. We also use active learning to smartly choose examples to be labeled by the user. And only the most important examples are labeled by the user, so we can reduce human effort. And since we're learning deep learning models, and deep learning is known for data hungry, we introduce another weak supervision algorithm that can automatically generate a lot of weak labels without human effort. So more technical details can be found in our Triple and EMLP paper this year. And I was planning to do a demo. I don't know whether I have enough time, but let me go to the results. So we have tested this method with multiple entity types, including dates, person names, organization names, and the machine logs. So the key takeaway from the chart here is that for our experiments, we can learn a very good parsing model for all the types here with very few human labels. In particular, we asked the user to label at most 15 examples. And after that, we have a model that achieves a FI score above 90%. So it's very effective. And this is another slide summarize our work on entity-driven normalization. We also have another tools, which is an earlier version of the one I just described. The difference is that the earlier version generate rules, and it's not necessarily deep learning is not necessarily always better than the rule-based approach, because as Yunyao mentioned earlier, we have a powerful framework, SystemT, which is highly optimized, and the Luster, which is the earlier version of the tool, generate rules that can run on SystemT. So if you have a task that requires high efficiency, rule-based approach is probably much better than deep learning approach, since we have this highly supervised, highly optimized framework, and they produce explanations. So, but the good thing is that we have two techniques, and it depends on the scenario. If it's a very complex scenario without any dictionaries, or the structure is very complex, we can use deep learning-based approach. Otherwise, we can use the rule-based approach. With that, I'd like to end my talk today. Thank you.
Okay, yeah, thank you for a very interesting talk. So we still have a few minutes left. Are there any questions for either Kun or Yunyao? Any questions? I have one, but I want to see if the audience has one before I ask mine.
I always appreciate your questions.
Okay. Okay, let me go with mine. Kun, you had a slide which had I guess the adversarial learning, where you were saying how with this particular architecture you were you were teaching the model to learn domain independent features. I was wondering if you could just maybe walk through that one more time.
Okay, so let me share my screen. Can you see it, my screen?
Yeah.
Okay, so let's see. Right. So here, the basic idea is that, since we are trying, for example, when do transfer learning, we have a source scenario and target scenario, right? So target scenario is the scenario we are trying to make prediction with, right? But unfortunately, we don't have any label data. So, but we have a lot of label data for a similar scenario, which we call the source scenario. So the idea is that when we train a transfer model, we provide the examples. We are sampling examples from both the source scenario and the target scenario. And each, for the entity pairs from the source scenario, this example, we have two labels. One is the class label, basically says that it's a match or non-match. And the other label is domain or dataset label, basically saying that whether this example is coming from DBLP's ACM or Google Scholar ACM, right? So that for the source, for example, from the source scenario, we have the two labels. But for the examples sampling from the target scenario, since we don't have any class labels, we have only the domain labels, basically saying that this is a data set coming from the target scenario, right? So when we train the deep learning neural net, we'll feed both examples into the training process. But when we compute the loss, for the entity pairs coming from the source scenario, we'll compute both the class label loss, as well as the domain loss. So if we don't have the gradient reversal layer, the pink part will trying to predict correctly that this data set, this entity pair is coming from which data source, right? If we don't have the gradient reversal layer, basically we are training two neural nets here and trying to correctly identify this pair is coming from the source scenario or the target scenario, right? Mm-hmm. So, but if we add a gradient reversal layer, if, for example, if the pink part during the training, the pink part correctly identify that this is a pair coming from the source scenario, but since we are reversing the gradient, then the rest of the neural net, when we train the pink part, the green part is trying to say that no, you are wrong. It's actually from the other data set. So every time the pink part make a correct prediction, we are saying that you are wrong. So this is a way trying to not encourage the green part to trying to differentiate the two data sets. So this is a way to shift the distribution of the source data to the target data.
Okay, so you're saying the green part will learn features that are not specific to any one data set as much as possible.
Right.
Okay. Okay.
Yep.
Any further questions? I know we're kind of at the edge of our slot, but any last questions for our speakers?
Thank you all.
Yeah. Okay, why don't we thank the speakers for a super interesting talk. Thank you very much for presenting in our seminar, Yunyao and Kun. Thank you. Great talk.
Thank you for the invitation. Okay. And you have our contact information. Feel free to reach out to any one of us.
Okay.
Thank you.
Great.
Bye.
Thank you. Bye.
Thank you.
Bye-bye.